Okay, good evening, everybody. I hope everybody's having a wonderful day. So today we're going to be talking more about hashing. Now, up to this point, we've talked about kind of the big idea of hashing. And we talked about last day about hash functions, what a hash function is, and what are some ways we can compute said hash function. So I talked, for example, about polynomial hash codes and how we can bring that together into a hash function. And we've also talked about some of these key ideas, like, okay, I have the hash table, and I can use this hash function to put records into the hash table, but I haven't yet really talked about how we're going to resolve collisions, which is one of the most important elements of our entire discussion. So now that's what I'm going to be focusing on while I incorporate some other elements of hashing, just to introduce you to some fun ideas that you can encounter if you explore this topic even further. So the first collision resolution scheme that we're going to be looking at is separate chaining. So suppose, just to give you a reminder of what we are dealing with, is I have a hash table. Now, to make this a little easier to see, rather than looking at it like an array, imagine I have my friends here. I have some friends here. And say they're going to the movie theater, and these are their seats. These are quite interesting seats. They're like buckets that just kind of hang out in them. And each of my friends, I say, for example, I use my hash function to tell me where I should put my friends. So suppose I have one friend here, this cute friend I have here. Say I put my cute friend here, it's based on the hash function that I may be using. And say I have another friend, my lovely giraffe friend. And I end up placing my giraffe friend here, based on the hash function. Now, suppose I have another friend of mine, this cute plushy kitty friend of mine, and say the hash function tells me to place this cat right here. Now, based on what we know about hashing, what does that mean? So what is just going to happen if I attempt to place this cat in there? And I'm not just saying make Pikachu into a mushapoo. I mean literally, like, what did we have a name for this? It started with a C. So what happens if I attempt? So notice I've run into a situation where I have a friend that wants to go into this spot, but it's already occupied. A collision, exactly. So now we got to talk about what we're going to do with our friends to place them into their seats. So separate chaining, here's the idea. It's a rather simple one, is that if a collision occurs, we just use more memory. So what we're going to do is we're going to consider each one of the entries or spots or positions in the hash table as a linked list. So they're going to have nodes. And here's the idea. I'm going to treat each one of these linked lists like if I ever need to put in another record, I just append another one. So for example, here's the idea for the collision resolution with my friend here with Pikachu. I make Pikachu a mushy shoe. So there goes my friend there. And suppose I have another friend, let's say this lovely seal friend of mine. And say, for example, the hash function tells me to place that friend here as well. Well, I would just place my friend on top as well there. Now note that when I do this, as I'm making sure to place my friends, and I make sure I don't put any duplicate friends in as I'm doing this. Because remember, a dictionary has this thing where we have to make sure that the keys are all unique, but all my friends are special, right? So they're all unique. So this is going to be the heart of separate chaining. So that's what separate chaining is. So to resolve any collisions, I just simply use more memory, and I just simply jam it in. Now you might ask, what does jamming it mean? I just simply mean, and I don't mean jam it in, I mean, I'm going to just simply have a linked list that's being maintained at each slot or entry of the hash table. And it's really quite simple. I'm just going to manage a linked list at each one of my spots in the table. So what do I mean by this? So if I want to get the data with a given key k, I use the hash function and I give it the key. So I compute h of k. And the data will be located in the linked list at that position. So if I have my table T, I access the position of h of k, and then there will be a linked list, or a list, just more generally. So just to do some examples of me effectively doing what I did to my lovely, lovely friends here. I'm going to go through some records and I'm going to place them into this hash table. So just as a reminder, in our hash table, we have a size for the table. I'm usually going to call that capital M to keep things simple. So for example, my hash table here will have 7 slots in it. And my hash function, just for simplicity, because we talked about how we would design the hash function, I'm just going to presume that we have some way of translating that input into something that's an integer. And what I'm going to have here is, whenever I give you k, it's going to be k mod 7. So if ever I go, remember when I say mod here, we'll see with some examples here. I'll walk through what mod is all about if you've never seen it before. We've seen it actually, we encounter it with the circular array list as well. Sorry, the circular array queue, my apologies. So we see that idea there as well. But I want to walk through just kind of applying this idea on a table with some records I have right here. So I have one with 21 as a key, 13, 12, 7, 3. So we're going to place each one of these into this hash table, each one of these records. So what I'm going to do is I'm going to start off with 21. So I give 21 over to my hash function. I compute 21 mod 7. Now, the natural question is, okay, well, what is that? Well, does anybody know what 21 mod 7 is? It's 0. It's 0. So another way you can ask this question is by integer remainder. So if I ask 21 mod 7, I'm asking you, what remainder would I get if I give the largest multiplicative quantity or multiplicative factor of whatever the value, whatever 7 is, for example, and ask, what's the remainder if I subtract off that? You can also think of it as repeated subtraction of 7 until I end up with something that's less than 7, at least for our context here. So 21 mod 7, notice that it's just 3 times 7 is 21. So you know right away that that is going to be okay for us. So I'm going to insert, so each one of these, I don't have them pointing at anything yet because I haven't created any new nodes. So I'm just going to put 21 in with its data v1. And right now I don't have anything else going on here. So far I have placed in 21. Now I have 13. So we ask, what is 13 mod 7? Now, one way you can think about it is, okay, well, 2 times 7 is 14, right? Well, 13 is 1 less than 14, so you know that it's got to be whatever 14 mod 7 is less 1, but you got to think about it from a wraparound standpoint. So I'm wrapping around because we talked about how we can use this kind of behavior to wrap around the array. So if it's 13, then yeah, exactly, and the chat is pointing it out. It's position 6. Because 14 mod 7 is 0. So that means that 13 has to be 6. Because it's 1 less than a multiple of 7. So I just insert this in. So I have 13, v2. So far I've done these two. Okay, how about 12? Now, naturally, because I said that, will you repeat, Professor, I'll repeat it again. So the reason why we place 13 here in position 6, in the list that it will be at position 6, is because, so let's just compute it out, because just for the sake of discussion here. So if I give you 13, now there's a couple different ways you could compute the modulus. And one way you could also think about this is, okay, so I ask, what's the largest multiple of a 7 that I can put into 13 divisibility-wise? Well, I can only put 1 7 in. If I put 2 7s in, I get 14. That's too big. So you'll notice I have 13 minus 7, and that is exactly equal to 6. This is in contrast to 14, which you notice that you can always write this in terms of, 14 well, I can always cleanly divide it, meaning I have 7 times 2, which is 14, which is just 0. So that's why it's in position 6. 12 very naturally would be in position 5 because it's 1 less than 13. So I just place 12 in here. So I have 12 V3. Okay, how about 7? Where should 7 go? Yeah, it goes right in 0 because remember, it's a multiple of 7. So now, this is where this collision resolution scheme is very useful for us. So notice now, remember, we're maintaining a dictionary here. So anything that computes the same value for our hash function might actually have the exact same key as ours, right? So this is something we have to be very careful about, right? So what I can do is I could just simply traverse the linked list and check if it matches my key, right? As I go along the linked list. And then I could just simply, instead of having this here, I could just simply insert it at the end of the linked list as I'm scanning across it. So, question, now whatever the size is, we should use that one in mod like 7. Yes, that's why the 7 is here. Yes, that is for the table size. Yeah, you'll find that the compression map is very naturally going to usually be the table size. Otherwise, we're not making full use of the table. So, anyways, so now we've got 7. Okay, now we just have 3 here. Now, the lovely thing is that 3 is less than 7. And if I were to check 3 mod 7, it'll just be 3. So I just place that here in position 3. So I have 3, V5. And no. So do you see how this resolves the issue of collisions? So now, if ever I want to retrieve anything from this table, all I have to do is I apply the hash function. And what do I need to do, everybody? What do I need to do? Well, we keep in mind that we can, if say for example, you can check the key, but all it really does is actually reduces down to a simpler problem that we've already seen before, right? So if I use the hash function, it tells me a position, right? It'll tell me which one to go to. So now, if, say for example, my hash function gives me a 1 at position 0, what am I actually doing now? I traverse the linked list, exactly. So now all we're doing is traversing a linked list. So if ever I want to retrieve the data for a given key, now I just have to do a search along the linked list, just doing a traversal of the linked list. Is that nice? So that means that many of the ideas you know about linked lists, they just apply here. It's very natural. So that's the big idea with separate chaining. So does everybody understand the main idea here with separate chaining is that I'm going to maintain linked lists at each one of the positions. And all I do is I create a new node and I insert it in at the end of the linked list, assuming I don't run into a duplicate key, right? So you'll notice that I have to scan through one of these linked lists, the one I get to for the hash function. I have to do that, otherwise I could introduce a duplicate key. So would this make the algorithm run longer? So there's a shortened, fun version of it. So we're going to see how this plays out in a moment. But I will tell you that, yes, one thing you'll notice quite quickly is that this actually should remind you of something that we talked about when I first started talking about dictionaries, right? We talked briefly about how we might implement a dictionary using a linked list. So that same symptom, the problem that linked lists have when I implement the dictionary, is very much present here too. But there's something that's nice about the way my hash table gets set up. So let me head over here and let's take a look at what one of these algorithms would look like. So let's head over here. Just going to move my friends over just a little bit. We'll we're not done with our friends yet. So we're going to talk briefly about put and remove. You'll get more acquainted with them on the next assignment. But what I want to do is I want to talk and focus primarily on searching, because that's the one I touched upon just a moment ago. So for putting and remove, it's quite similar to inserting and removing a node at a linked list at a given position. I hope everybody can see that. It's very similar. So I want to highlight specifically the get operation. So we're going to talk about the get operation here. And so let me walk you through the get operation. So imagine I have it where I give you a key, and I want to return back the data for key K for that record, and null if that key is not in the table T. So what I first do is I apply the hash function to determine the position that I need to index into my table, and that gives me back where the head of the linked list would be P. So keep in mind that the head of the linked list could be null, just if there's nothing there. So that means that we're going to have to do a traversal of the linked list, and all I'm going to do is I'm going to modify how you might traverse a linked list using a while loop. So all I do now is I just simply say, okay, if it's not null, that means there's a node there that I can examine. Then I could examine its key, and I check if it's not equal to K. If it's equal to K, then we're done, right? I don't need to do any more traversals, any traversing any further down the linked list at all, right? So if it's not equal, that means I need to go to the next node and see if it's there. And if I don't find a match again, I just keep doing this over and over again. So notice every time I just get the next one, and I examine these two conditions up here. And you notice that I'll leave this while loop either when I get a match or P is equal to null. So it's only two possibilities that can happen here. So if P is equal to null, then you know, hey, look, it's not there. So I better return null. Otherwise, I'm going to give you the data. So this is how you'd perform the search. It's really nice. You'll notice that it has a lot of bits and pieces you may be familiar with from playing with linked lists. So, are there any questions about the pseudocode before I proceed with our analysis? So I'm going to keep it a little bit more higher level just for the sake of time, but I do have full explanations for these in the notes. So we're also going to walk through how I identify the number of operations. So if there aren't any other questions, let me proceed with that. So first, let's focus on the worst case analysis. So first, remember, I have the computing of this hash function, right? Now, if you use the hash function, would it be possible to quickly run through the algorithm, please? So we already did it, believe it or not. We already did it. So all I do, so I'll do it while I do the analysis. Makes it a little easier. So I compute the hash function. We've seen how we were able to achieve this in constant time. So indexing into an array can be done in constant time. So all of this takes some constant C1 many operations, right? So it takes some C1 many operations. Now, to get the next node, well, that's some other constant number of operations. So recall here, all we're doing is once we've identified the linked list we would like to explore or traverse down, we just simply go down node by node, seeing if we can find the key. If we find the key, then we leave the while loop because it will fall. This condition will become false. So it means that it is going to be equal to key K. So we ask, how many times does this happen? Well, that's going to be an interesting part of our discussion, which I'll come back to this one in a moment. But then we have this last bit here. Well, evaluating if P is null or not can be done in a constant number of operations. Returning null takes a constant number of operations. Getting the data from a node that I have direct access to takes a constant number of operations. So there's C3 many operations that happen here. Now this is where things get interesting. So as it was alluded to in the chat, notice here, what could happen if one of those lists over there contains every single record? So it's possible that somebody could, conceivably speaking, have it where the hash function places all the records along one of the linked lists. So it seems like if I wanted to determine the number of iterations of how many operations are happening with this while loop, it seems to be something a lot along the lines of C2 times the length of the list. Because the length of the list, remember, it's possible that I attempt to try a key and it's not there. But that means I have to scan through the entire list. But what's the length of the list? Well, at most, so let's focus on just the idea that it's just the length of the list for now, and then let's proceed, okay? So we know that this algorithm, if I add up all of these, I'll have C1 plus C2 times the length of the list, then I have plus C3. There's my complexity function, but I still haven't really figured out what I'm doing with this yet. So we have something that looks along the lines of C1 plus C3 plus C2 times the length of the list. So, question, what is this in terms of big O? Just keep it very simple. Well, it seems like the length of the list is not a constant, right? So we know it's going to be something like, actually, let me just switch from the blue. Let's go back to the black because it's a little hard to read when it's in blue like that all the time. So we know we're going to have something that looks like big O of length of the list. It'll be something like this, right? Big O of length of the list. So, as mentioned, it's possible that all the keys hash to the exact same position, which is conceivably possible in the worst case. So, that means the length of the list is in fact going to be n, right? So in the worst case, you can have it where it's big O of n. So in the worst case, performing my search here, as would be the case with put and remove, all of them in the worst case run in linear time in the worst case. So question, though the length of the list are different for different hashes, it wouldn't make it any difference, right? It would be big O of n. Yeah, it would be pretty bad luck, right? So keep in mind that we're just imagining a scenario where the hash function could conceivably get it so it always places it in the exact same spot, which is really unlucky, right? But keep in mind that it is possible. It is possible under the schemes that we've seen so far. It is possible. Now, you might ask, okay, so what does it mean in the average case? And I'm going to talk a little bit about this, but here's the intuition behind it, which I'm going to explain in a moment, is that the average case for my get is actually constant time, which I'm going to explain actually now. But before I get to that, I want to touch upon one important drawback of separate chaining before I proceed to justify why this would be true. So, the one big drawback of separate chaining that I really want to touch upon is the whole idea in our scheme is that we use memory to help speed up some of these operations. But what if I don't have all the memory in the world to keep creating more and more nodes like this? So that could be a drawback for separate chaining. So a drawback is somebody might tell you that it uses too much memory. So if you really care about memory requirements, separate chaining might not be ideal. Why do we return when p is equal to null? So remember, when p is equal to null, that means that this condition failed, right? That means that p is equal to null. But remember, it's just a linked list, right? So if I get to the next node and it's null, that means I scan through the entire linked list. That would imply that there is nothing that we found because it didn't falsify that second condition over there. The one saying that I check the key and if it's not equal to k. But if it's equal to k, it'll falsify the second condition on my while loop over there. But yeah, so the whole idea here is that this checking if it's null or not is actually a test to determine if you need to return null or not, because you have something if you stopped before you hit null for p. Well, somebody's asking, would the worst case time complexity, should it be quadratic? Because we have to scan every hash data. Now, remember, I use the hash function. Actually, let's go over here. Let me just reiterate something here. So remember the big idea here for our get. So remember, when I attempt to find a record, what I do is I apply the hash function, which is achieved in constant time. That gets me to one of these lists. It gets me to some list. It could be this, it could be up here, it could be here. And then all I do is I traverse through the linked list. And you know that traversals of a linked list could surely be no longer than big O of whatever number of elements there are in the linked list, right? That's where the linear term comes from. It's not quadratic, because examining this takes constant time, because I have direct access to it when I get there. That's a wonderful question. And now, another question was like, why can't we use dynamic memory? We can. In fact, this scheme uses dynamic memory everywhere. So I create an array of table size m. So I have m as the length of the array, and each one of these is a node that I create every single time. So how can we run out of space? Now, theoretically speaking, our model computation never could, but in practical settings, you can. So suppose that for example, we talked actually about our first example I introduced where I had a lot of student records. I think I had 10 to the 9 student records. Well, suppose that all of these student records, each one say the data was located in that. Say each one of these, every time I build this hash table, each one uses a large chunk of memory. And say I have this large table I'm trying to maintain while I want to do other things with all that data. It's possible that I might use too much data. I might not have enough space. Now, for people in this day and age, memory seems very, very cheap. There was a time where that was not true. In fact, memory used to be very expensive. So for us, it's a little bit easier to imagine a time where we could just keep using memory. But surely there's a finite number, even on a tangible computer, of how much memory you have. So that's why we have to keep that in mind, is that we don't have an infinite amount of memory in practice. No, anytime. That's a wonderful question. So now I want to talk about a concept that's going to help me justify why I'm telling you that the average case for separate chaining is actually constant. In fact, it's a little bit more exact than just that. So I can actually give you a rough idea of how good it is. So let's talk about this idea. So just to summarize, just before I get too ahead of myself, if I have get, put, and remove, so by very similar reasoning that I gave before, all three of these, in the worst case, performs big O of n by the same rationale. So you just attempt to try to find it. It may not be there. But you have to scan through and check. But it may be possible that you end up with a really, really bad hash function. And it might not, it might literally be where, conceivably speaking, somebody gives you some very inventive sequence of keys that lead them all to go into one of our linked lists. But on average, I want to stress that on average, all of these operations, under the assumptions you have a good hash function, so that uniformity assumption I'm making, if you have a good hash function, all of these will end up being big O of 1 on average. Now, I want to talk about a big idea that helps me justify this idea in terms of separate chaining, is the idea of load factor. So I'm going to talk about this idea called a load factor, and it should help me give you an intuition behind where this comes from. So question, I'm confused, like when we call h of k, it gives us a linked list, only one at h of 0 or h of 1. Yeah, it gives you a, remember, the hash function gives you a position in the table. And all we're doing is we're indexing into the table to get the linked list head, right? If it exists, it might be null. So we have this idea of the load factor. I'm going to call it alpha for the sake of our discussion here. It's going to be equal to n, where n is the number of keys stored in the table. So this is the number of keys in the table. And capital M is the table size. So at the heart of this discussion I'm going to have is this idea of load factor. So I'm explaining that right now about the average case. So I'm explaining it using load factor. So one thing I need to stress is at the beginning of our discussion about hashing, as I said that n, this lowercase n, is less than or equal to capital M. Now, if we have a good hash function that abides by the technical assumption I gave you, this uniformity assumption, you got to imagine it like this. So I have all of my hash function. Suppose it's able to uniformly spread the keys across the table. Now, on average, what would happen is, at least this is what you would expect, is that if it's able to uniformly spread them, you also can imagine it like I have my array, but on average grounds, you would expect that each one of these elements would fit into a spot without having to rely on a collision. But let me explain how that relates to separate chaining and this idea of the load factor. So I'm just planting a seed for something I'm going to explain in a moment. We assumed n is less than or equal to capital M, but in separate chaining, it is possible for n to be greater than m. So the time to traverse a list on average is going to be something like big O of 1 plus alpha. So let me give you some intuition behind these two pieces to this discussion. So the first thing is there's this idea called the load factor, right? If I know that n is in fact less than or equal to capital M, the idea is that if I have all my slots in my table, on average, what you should expect is something along the lines of, as I use the hash function, which has a uniformity to how it places records into the table, it should do something along the lines of filling in something like this. If, say, the load factor was less than or at most 1. Now, if the load factor becomes higher than this, so suppose it's actually going to be something a little bit more than this. And I must stress this 1 is here because the alpha here might be less than 1. But it also serves a statistical purpose that I won't have the ability to talk about here because of just the background required to discuss this idea. But suppose that I have my load factor and say I have more elements than those that are in the table size. So I see an interesting comment. So it is the load factor for each key on uniform distribution. Yes. So notice that if I have more than m slots, what happens is you should expect it to layer on average. So the key phrase here is on average. It's on average, you should expect it to layer on top of each other, like if you could imagine this like a layered cake, where this is one layer of the cake, this is a second layer of the cake, here's the third layer of the cake. So if, say, alpha was, say, greater than or equal to 3, you should expect them to be distributed in a manner so that roughly it fills it in, kind of like what I've just done on the board here. So when it's laid out like this, do you see how the load factor tells you? So notice that if this is m here, and if I look at this ratio here, say if I have 3 times as many elements, this is just relating to alpha. So I include the 1 there because I'm talking about the time to traverse a list on average. So naturally, I have to examine the list at the beginning, right? Before I start going and examining the elements, which these would correspond to. So each, if you read them vertically. So this is the idea behind the load factors. The load factor actually has a very close relationship with the performance of separate chaining. So to give you an idea of how you might balance this issue of the load factor with the size of the table, what I would like to do is I would like to make it so that there's a few of these collisions that can happen. So now naturally, that means that there's got to be some relationship that the table size has with the number of elements, at least in practice. So if the number of hash table slots or positions, I'll just call them slots to keep things simple. If the hash table slots is at least proportional to the number of elements or keys, to the number of keys or elements or records, whatever you'd like to say, records in the table by some constant, then if you look at the load factor, if you make sure that this ratio is always a constant number, what does that mean alpha is in terms of big O? If it's always going to be that this ratio here is going to be, what is that going to be if I assume that it's always that the number of table slots is always going to be at least proportional to the number of keys by some constant? So they're going to be proportional by some constant. Yeah, it's going to be constant. Exactly. So then alpha equals n over capital M is big O of 1. So you might ask, Dan, so you're suggesting that we should decide maybe on some constant, which would be reasonable for us to presume on average for our collisions, right? You almost think of it like a layered cake. I decide on some constant, and I say, okay, it's good enough as long as it doesn't have too many collisions in it. So the whole idea here is I'm going to make some decision as long as it's some constant, like 3 times the number of table slots. So for example, I have 3 times capital M here, for example. You make some assumption that it's some constant times that. As long as you make sure that the number of elements doesn't exceed this amount by some proportion, so they say roughly in this proportion by some constant, we're okay. We can actually get some nice results regardless because the load factor will remain constant. However, if I don't do anything with the relationship between the load factor and the number of elements, this thing could still keep going, right? So it's still going to be true that on average it's this, but I would like it so that this load factor isn't so wild and erratic. So I would like to make it so it's something that's proportional to the number of elements I should expect to be there. So this is going to give you some insight into how I should design and the size of the table. So just to give you an example of what you would do, so if the performance degrades, so this would be a practical consideration. If the performance degrades, and the load factor exceeds a constant value. So this is a constant value that you decide. Increase the size of the table. And rehash, which I'll explain what that is in a moment, rehash all the key value pairs into the larger table. So I must stress what exactly I mean by rehashing. So, you know how we talked about if you run out of space in an array, when you're dealing with some data structure. Like if my array becomes full, what is something I do, right? I resize the array by creating a new array, and then I make that one longer, and then I copy all the elements into the new array, and I assign that to be what my array is, right? So, what happens here? Now notice that I can't just simply copy them over into the new array. I have to actually compute them all with the hash function. So essentially I have to rebuild the entire table with the much larger length for my new array or table. So when I do this, this is a very expensive operation because I have to rebuild the entire data structure. So this is something you want to highly avoid doing. So doing this is expensive. So usually a good idea in practice is to decide on what this constant might be in advance based on the input data you have. Yes, exactly, because the positions might change from the ones that if I were to directly copy them over, the hash function may not work anymore. Instead, I may have them in different spots. But yeah, it's a wonderful observation. So there's a couple questions. So let me just reiterate what I mentioned here, just because I know my writing here is a little bit, looks like it melted in the microwave. If the performance degrades and the load factor exceeds a constant value, increase the size of the table and rehash all the key value pairs into the larger table. So now we have a couple questions. If alpha is 1, is it big O of 1 plus alpha? Shouldn't it be big O of 2? Remember, big O of 2 is big O of 1, right? So if I give you 2 and I asked you to prove that 2 is big O of 1, you could actually prove that because it's just a constant. It's a constant function. So remember, it's just a constant. So it just gets, it's all just lumped into some number. So somebody's asking about, I don't understand why we use the load factor. So the load factor tells us a ratio of how many elements are in the table versus how big the table is. So in separate chaining, on average, under the uniformity assumptions I've been making, the load factor tells you on average what you should expect for the number of collisions. And keep in mind that this is the length of time to traverse the list on average. So remember, I still have to examine it at some point, right? I can't just say, oh yeah, no, I'm magically only looking at the nodes. I'm not actually examining what's there. So I have to still perform some constant number of operations to achieve this. The point is that there's actually a relationship between the load factor and on the average number of nodes you'll have to examine. So almost like to think of it like they're nicely falling into the right spots so that they layer like this, like a layered cake. So it's really nice. But like I said, in practice, you want to be mindful of the size of the table when you do this. Because if, say for example, your table's not really big, what happens is this layered cake becomes even more layered, has more layers to it, which means that the performance might degrade over time if you have more and more records placed into this dictionary, if you think of it as a dictionary. So you want to try to strike that balance in practice, is how many collisions on average would I like to have? Remember, it's still on average. You could still have more collisions that happen. It's just statistically speaking, on average, it's going to be rather nice. It's going to relate to this load factor. So, are there any other questions about this idea of the load factor and how it relates to separate chaining? So you're going to find that when I show you the other collision resolutions, that almost all of them are going to keep under this assumption that n is less than or equal to capital M. Because the other schemes I'm going to use aren't going to use more memory. They're just a little bit more complicated. But the idea, once you understand it, it's really nice and simple. Okay, give me 2 thumbs up if we're ready to go to proceed to our next collision resolution scheme. Okay, wonderful. So why don't we talk about the next collision resolution scheme I would like to talk about. So I've talked so far about this idea of separate chaining. Now, in separate chaining, I use extra memory to resolve the collisions. I would like to find a way to do this without having to consume so much memory. So we gotta have a different way of resolving the collisions if that is the case, right? I can't just simply stack my friends on top of each other. Suppose that my friends really don't care about becoming a mushy chew. Sorry, I was just sort of recollecting to myself why I don't even say that. It's funny. So let's talk about, obviously not our friend getting squashed, of course. So let's talk about what I'm going to refer to as open addressing, which will contain the last 2 collision resolution schemes that I'm going to talk about. So if space is expensive, so if space is really cheap for you, separate chaining is wonderful. So just be aware that it is nice. It's just that it uses lots of memory. And if you really care about your memory resources and you want to keep things as cheap as possible for your memory usage, it might not be ideal if you have very tight budget or constraints on how much memory you can use. So if space is expensive, separate chaining may not be ideal. So what does that mean? That means I'm going to use the table itself, but I have to provide you some consistent way of inserting, searching, and removing from the table. And it has to be so that I can always search for my records, that I can always insert one's new records in without throwing a duplicate key into the table, and so on. So if we want to use M slots, so these are positions. So I'm using the word slots. I think it's a little bit more appropriate if you think of it like a table. They're just positions in the array. M slots of table T. We must determine a consistent way to insert into T. So if we want to use M slots of table T, we must determine a consistent way to insert into T. So I must stress that as n is going to be less than capital M. And must stress that in these schemes, if ever the hash table becomes full, you'll have to rehash the entire table. Just be aware of that. So, what does that mean? It means that the load factor is always going to be less than 1. So it means when you talk about things in terms of average case, you should expect that the behavior of it on average will be that we don't really run into collisions, at least on average case. Just think of my example over there where I had the layered cake. You would have it where there's only one layer to the cake. But the idea here is that I need to do something more because I can't, obviously I still have to deal with collisions. That's going to be a problem for us. So I'm just giving you some intuition behind some of the calculations here because the analysis for doing these average case analyses are a little bit more complicated than at this time that I could present to you. So here's an idea. So before anything, I'm just going to make a remark just for the ease of my discussion here. I'm going to assume that an empty table has null references or null pointers. So I'm just going to assume if I have an empty table, it's just full of nulls. So what's going to be the idea here is I'm going to do something in a way that's rather, at first this will seem a little bit strange. So here's an idea. Here's an idea. So of course we have the hash function. We can always check position T sub h of k, just like we did with separate chaining, right? But if null is there, what does that mean then? If there's just a null there, then most certainly I could just place the record right there, right? That's all I have to do. It's safe. There's no collision that happens at this stage. It's just an empty slot. It is safe to insert into the hash table. However, we have to deal with whatever happens if it isn't null. However, if T sub h of k is not null, I'm going to be introducing the idea of what we call a probing sequence. So we apply a probing sequence, which I'll define in a little bit here. A probing sequence. To tell us the next position to check. So we're going to explore two kinds of probing sequences, and these will define the collision resolution schemes that I'm going to suggest for the remainder of this discussion. So let me just summarize the big idea here, and I'm going to tell you what those two are as we move over here. So you may or may not have heard of these ideas here before, but there's two main kinds of ideas with open addressing. So the first one is what we call linear probing, which I'm going to start, that's the one I'm going to start off with. And as the name suggests, it's going to involve us sequentially going through the table and try to find a spot where it fits. The second one is what we call double hashing. And the idea here is that we use a second hash function to resolve some issues that linear probing has, which we're going to talk about that here. So here's the collision resolution that we're going to use. So just like I talked about collision resolution for separate chaining, So in open addressing, the idea is to probe to find, my apologies, there was a little crinkle there, is to probe to find the next available slot of T using a probing sequence. So when it comes to the idea, I'm going to be defining what I mean by this shortly. So let's talk a little bit about this. So the first one is what we call linear probing. So we have linear probing is the first of these two that I'm going to talk about. And I'm going to walk through the idea that I've talked about over here in the context of linear probing here next. So let's talk about linear probing. So on a collision, so if we have a collision that happens, on a collision, check the next successive, which I'll explain what that means in a moment, successive position, modulo M, so mod M, until a spot to put the key value pair is found. So just to explain what a probing sequence in this case would be. So I'll explain what this probing sequence business is all about once I've defined what it is for linear probing. So first you check position h of k. If h of k is null, then you know you can safely place your record into the hash table. Now, if there is something there, meaning that it's not null, then you simply will just go to the next position. You check h of k. I apply the hash function given key k. So I apply this plus 1 mod m. Now, if there's something not there, I would just simply place the record in that spot. If it is not there, I need to apply the next position. So I would check h of k plus 2 mod m, and so on. So all I do is I increment through the table to each successive position. What we do is what I would describe to you is a hop. So one thing I do have to make a remark about, just before I explain this probing sequence here, is note that linear probing does not require m to be prime, meaning it's not a prime number. It doesn't have to be. However, in practice, you usually want it to be. So, linear probing will work regardless. One of these collision resolution schemes I'm going to give you requires that the table size is a prime number. So, let me explain how this will play out. Now, it's kind of funny to imagine your professor pretending to be a bunny rabbit. So imagine I'm a bunny rabbit. And suppose that I have all my places I have to go put, say if we're talking about Easter time, and I'm like the Easter bunny going around putting eggs into spots. Now, what I would like to do is try to find the first available spot I can place an egg into a spot. Now, if I don't see a spot, I need to hop over to the next available spot and see if I can place it in there. Now, if there is a spot for me to place an egg in, I can do that and I'll be done. But if there's nothing there, I'm going to hop to the next available spot and I would check there and see if I can put my egg in that spot. And I would keep hopping. So effectively I do these hops through the table. So I start at h of k. If I cannot place it there because that will cause a collision, I hop to the next spot. If there's not going to cause a collision here, I would place it in. If it isn't, then I need to hop. So I do a hop. Just like I have rocket boots on. so I do a hop. But these aren't really good rocket boots, okay? They're just like I'm a little bunny rabbit. So I'm a little bunny rabbit. I hop until I find the next available spot. And that's what linear probing is we go through the table finding a spot that's the next available one, and we apply this probing sequence. This tells us the locations to examine, and we keep doing this until we examine the whole table. So, are there any questions about where we're going with this? So, if I have a table, all now I have to do is I use this probing sequence to follow through and find a spot, whether I'm doing an insertion, I try to find that spot where it needs to go in. Just like me being the bunny rabbit, I try to find a place to put my Easter egg in, for example. Yes, so when I mean successive, I mean you try h of k. If you fail at that, try the next position. If you fail at that, try the next position. And each one of these is a hop, like me being a bunny rabbit. So how will the function remember where to put the data? Well, remember, all we do is we compute the hash function. So how does it remember? It stores the records in the table, right? So what if we don't find the spot, or if that's impossible? So remember, we're going to do this while we go and explore the whole table. So if we fail to do this, we know right away we failed at doing an insertion, for example. But if we go through the entire table, most certainly we failed to find it. So for some of our operations, that really matters, because sometimes we make the assumption that the record is in fact there for a given key k. For other ones, not so much. It's just that you may actually explore the whole table, and that means that it's just simply not there, right? So let's talk about get first. So let's talk about get. So you apply the probe sequence. Follow until key k is found. And return null if null is encountered. Or all of t is checked. Because it's possible when I make these hops, when I'm trying to find a record with a given key, I might hop to a spot that has no record in it. So that tells me right away it doesn't exist. But it's possible I have to hop through the entire table trying to find this key. So that is something you have to be wary of. So let's talk about how we would do this. So let's talk about the get operation over here. Actually, I think probably it'd be better we do an example. I think that will probably be more useful for our time. So let's do an example. So we'll do some insertions through put operations. Actually, let's do get first. Let's just do get first. Because since I started talking about get, let's just do that before we get to put. I think that's easy enough for us to do. So let's talk about get, seeing as we understand the idea. Just think of your professor as a bunny rabbit. It makes things much easier. Just don't think about it after you have a whole bunch of candy. I will warn you that you can get some really nasty nightmares doing that. So, I'm going to give you the algorithm. So I'm going to give you get, given a key. So remember the input is a key K, and the output would be the data for key K, or null if K is not in T, not in the table. So I'm going to start off by using the hash function to determine the position that I will be beginning at in the table. So I use the hash function first to figure out a position I'm going to call pos. And I'm going to make it a counter variable called C. So this is going to be a counter. And this counter's purpose is to tell me how many elements I've examined, how many slots I've examined so far in the table. This will be very helpful for me to know if I've examined the whole table. So I'm going to use a while loop because I don't know how many elements I'm going to have to examine here. While I check, while t sub pos is not equal to null, and t sub pos dot get key is not equal to k, we're going to do the following. Yeah, it's a little bit verbose like that. Okay, good. I just fit it in there. I was just looking at my camera over here. Yeah, I was like, oh man, that's a little slick there. So just to reiterate, while t sub pos is not equal to null and t sub pos dot get key is not equal to k, we're going to do the following. Because remember, if it's equal to null, we're done. That means it isn't there. If I find the key when I'm examining these entries or slots, then I'm also done because I found it, right? So one of these two has to break at some point, but there's also another issue where I might examine the whole table, but the problem is every time, you notice how I was the bunny rabbit, I hopped to each successive position. There's nothing really to stop me from keep doing this, right? You don't want to see me hop. Okay, maybe some of you might want to see me hopping around for 10 hours straight until I just get tired and fall on the ground. I don't know. It could be an interesting thing to watch. I don't know. But the point is that I need to, if I don't find a match, I'm going to perform a hop. So I perform a hop. So I'm going to increment my position by 1, and I apply mod m to that. This is to ensure if I go all the way to the end of the array, I come back around to the first position. I would make a compilation of that. Hey, look, that sounds pretty epic. So if I increment the position by 1, that means so when I failed this test, meaning I didn't find it, that means I've examined one more element. So I'm going to increment C by 1. And naturally, if I examine all the table entries, how many table entries can there be at most? I'm looking for a variable. Something involving the table, right? It's capital M. So you know that if this counter variable, if I fail to make this match, M times, capital M times, you know right away you examine the entire table. So I'm just going to add an if statement inside of here just to make sure we have some way of breaking out of this process. Because otherwise I'm just going to keep hopping around in circles until I don't know what happens. The point is I'm just going to keep, at least theoretically speaking, I would hop forever. Which, I don't know, could go really well with the chicken dance music or something. I'm not quite sure. So then I'm going to return null in this case because I've examined the whole table. Now, if this while loop has one of its conditions falsified, that means either this became, the t sub pos is equal to null, or it's that I actually found the key. There's only two possibilities here. If that is the case, I'm going to check if it's null. So if t sub pos is equal to null, then I just know, okay, I failed to find. I didn't find it. So I just return null in this case, because I didn't find it. Otherwise, sorry, I was a little squeaky. Return, otherwise I found it. So return t sub pos dot get data. So I get the data. Yeah, there's no linked lists here. Everything is contained within the table. Yeah, everything's contained within the table. So I'm actually storing directly the records into the table. This is in contrast to separate chaining where I actually maintain lists. Instead, now I have it where it's just simply going to store them directly in. So open addressing schemes always have this setup where you're just going to have slots. You can place the record in or your element in, however you're using the hash table. It's all going directly into the actual table itself. So in this sense, it's a pretty pure version of a lookup table. It's just the problem is that now the elements, the records I'm trying to find might be scattered throughout the table, and I have to use these algorithms so in case I run into collisions to find them afterwards, right? So I'll talk about the collisions and how this gets applied, because remember, this tells me how I can retrieve them. So the first thing I want to point out for you is just time complexity. Remember, computing the hash function takes constant time. Notice that this is really just saying to you, hey, look, I'm going to have to perform some number of iterations in this table. Now, the only way it's possible I could have to examine the whole table using this algorithm would be if the table's completely full. That's the only way I could have it where this check happens. So either this can happen, or it's just simply that I examine every possible slot that has something in it. Either one yields the worst case here. So if you were to derive this, which I have the analysis in the notes, just because we're kind of running low on time here, the worst case is going to be big O of n operations for the reasons I've just stated here. So, you might ask, Dan, what's going to happen with all of this? Well, because we ran out of time here today, when I come back next time, I'm going to show you how we put records into the hash table. We'll do an example, and depending on how much time we have, I'll show you the pseudocode for it, because once you see how the insertions are done, you can really quickly see how the pseudocode should be. But we'll talk about insertions and removals, then we'll talk about double hashing. And that'll be basically the last bit of our hashing discussion. And I'll have a couple things I'll bring up about load factor again. So that being said, I'm going to stop right here. And I want to say thank you very much and have yourself a beautiful day. I'll see you later. I guess a beautiful evening. Beautiful evening. I'll see you later.